it should be overestimated, the power supply. So at least twice. So if you're from your calculations you get let's say 2 watts. That's your embedded systems will need over various power supply pins. Then at least you should multiply it by 2 at least. So designing a power supply exactly at the point, it's usually the life shows that it's pretty risky. So here multiplication by 2 is a good idea, roughly plus minus. If you have a chance, you can even multiply by more. So of course it depends on the power. In case of the power supply, again, we did the analysis some time ago, so that it's either linear or switching options that we have today in case of the power supply, in case of the regulators themselves. Normally today we are rather going into switching world because the switching delivers us more, so it gives us more capabilities and delivers higher performance, so higher efficiency solutions we can have. So with switching supplies, reaching 90% efficiency of power conversion is possible. So think completely out of question in case of linear, but that's theory. From practical point of view, the linear power supplies, they have some advantages, maybe not a lot, but they have some advantages. And the major one, in case of prototypes especially, is their simplicity. So they are of course heavy because of the transformer itself, but they are simple. So you just need a transformer and some rectifying bridge capacitors, and then a regulator, and it's done. So of course, if you design something new, then switching regulators, switching power supplies and switching regulators are offering more, very often today for less. But if you want to do something very fast, if you want to have rapid result about your prototypes, then the linears with linear power supplies and linear regulators cannot be crossed, to be honest, and very often they are used. The linear regulators have also, from this perspective, one very important feature. Of course, they are cleaner. The power supply is a bit cleaner, so we are missing so there is no RF noise, which is the case in switching regulators. In linears, we don't have this noise. We have instead a very nasty 100 hertz or 120, depends on the region in the world, ringing. But putting this aside, the linear regulators, they are tougher to break. That's again, from practical point of view, it's not negligible, I'd say. In case of switching regulators, okay, if they have security circuitry included, then okay, that's fine. So you can shorten them, you can overload them, they will simply switch off. But still, switching regulators are much easier to be broken than the linear ones. So again, summing up, switching is better in general, but it's more complex. So for simple applications, the linears have an edge over them, as well with the ripple and noise generated. So linears, if you make a very good capacitance, because here on this chart, it's a bit exaggerated. So maybe not exaggerated. The time scale here is just 100 microsecond, which means that the whole timing of the picture you can see is 1 millisecond. So for linear, that's not a problem. So linears, they don't have the high frequency noise, but honestly, the low frequency, so this 50, 100 hertz, especially if you intend building audio applications, then this is again an important disadvantage of the linear power supplies and linear regulators. power supplies, because the regulators don't have this problem, but about the linear power supplies. The regulators are working fine. So in case of linear, is the problem about the linear regulators, as you should remember, have two problems, two disadvantages. So the first one is that they hit very much, because there's a lot of power being dissipated, and here naturally, don't forget that if we have this regulator, linear one, and there is a V in and there is V out, so the difference of voltages, so delta, so delta V, maybe not this one. So the power, the voltage difference, so V out minus V in, or maybe this way, the whole voltage difference will be the whole voltage difference will be visible on the regulator. And if we have a certain current flowing, so the power loss, of course, will be dependent on this, on the current, and on this very large voltage difference, meaning that the power dissipation, the power loss of the regulator will be pretty high. That's the first problem. And the second problem about the linear regulators, so this problem can be overcome by making V in as close to V out. Yet to have this capability, we need to have a so-called low dropout regulators, because they are on the market, two types, standard ones and low dropouts. Yeah, question two. Maybe you have met this problem. What's the minimum difference of V in to V out in standard linear regulators, and what's this in low dropout? The numbers. What are the values expected here? Who knows? Who make this kind of regulators in practice? Like 78XX regulators, or LM317, for example.
1.25 volts.
For a low dropout or for regular?
Regular.
More, usually more. Sometimes, so 1.25 volts you can meet at low current, because it's current dependent. Safe value is above 2 volts. And for low dropout? At low current, low dropout may require as little as 50 millivolts. For high current, low dropouts usually are about 200, 300 millivolts. So that's the difference. That's the difference. And if you intend using linear regulators to get fine output voltage, then be careful. So try to have this in mind, that low dropouts are here advisable. Low dropouts are widely available, so there is no problem of availability. They are, of course, more expensive than the standard solution because they are better. But in single units, if you build some small short series, that's not a problem. So the pricing is not an issue. So generally, we should avoid using standard regulators. Rather, in my opinion, we should use by default low dropouts. Then low dropout is simply better than, only more expensive than standard regulator. But that's the problem number one. Problem number two with regulators is that they can make only lower output voltage than input. So V out is always lower than V in. Lower but larger than zero. So that's the problem. So we have situation 0, V out, and V in. Yeah, of course, it can be a coil here. How to overcome this issue? The only way to do it is to deliver higher voltage. So there is no option. In case of switching regulators, we can play it. So we can generate higher voltage, sometimes much higher voltage. We can generate negative voltage. so we can change the polarity. Here, no. So again, this is up to your design. Which solution you would choose. These are the options. In case of switching regulators, they offer today on the market. There's really a variety of this regulators. We talked about it. This slide I tried to show you before. So they are regulators with really very fantastic efficiency. So exceeding 90% with very small footprint of the whole regulator. It's just that we need to still design it, and we need to still make some protection and take care about the noises. So in general, again, switching regulators as well are better than linear, but it really depends on that, on your perspective a bit. Normally, and that's surprising a bit, choice is difficult because of the huge variety of DC-DC converters. And that's kind of difficult, in fact, really, to decide which regulator to use. In case of linear world, it's much simpler because there is, you've got this LM317 for normal regulators. You've got the regulators like LE33 or LE50, something like this for low dropouts. Then you just decide on the case, but some regulators like this LM317 or 78 family, 79 family for negative regulators, regular ones. They exist in various cases, so then you just choose the case adapting to the expected power consumption, and it's done. So there is not much difference in linear regulators. Thus, then in the switching regulators, there is such an abundance of the regulators. Then sometimes it's you're just sitting and skimming through the documentation and thinking, oh gosh, what should I choose? So they are available and they have similar capabilities, but they are different here and there. So different case, different capacitance, inductance, and component count necessary. Yet, in order to choose it, I would recommend, first of all, choose the regulator working with very high frequencies. Very high frequency means the necessity to use better components, but 1 megahertz today is not a problem unless you want to build a supply or regulator delivering 100 watts plus. But if you want to do something smaller, a few watts, maybe 10, 20 watts, then 1 megahertz, finding a transistor and elements capable of switching at this frequency shouldn't be a problem. Because at this very high frequency, even if we have the noises are easier to be eliminated in real applications, especially in noise-sensitive applications, so sensor connections, sensor conditioning applications. Second thing, possibly low component count, because then for some reason the market really throughout the years there were this market has been heavily developed and has been significantly growing. So the market of DC-DC converters, switching DC-DC converters, and you can still find in the market the construction stated 20 years or something like this, requiring 20 components, but you have a switching regulator and 20-30 components around. So my idea is to search for something simple, smaller component count, fewer problems in the future. Then another from practical remark, small size, but without exaggerations. Very nice English word, without exaggeration. Really, unless you have the capabilities, that's not the best idea to go into a very tiny CSP or very tiny LGA cases. BGA are not that bad all in all, but still in case of the regulator, I would think twice of using BGA case. Of course, sometimes we have no choice. Sometimes it's just that there is just one component, one case, and we have to, like this one, QFN, and we have no option. But still, if there are two tiny cases, so which are 1 by 2 millimeters, so 2 by 2 millimeters, so then I think about it. If this is really a good idea to go into such a super tiny case, because with super tiny cases we've got two problems. Problem number one is difficult to assemble, and then it's very easy to have the assembly issue with this kind of cases. So like some short circuit or some broken pin. But the second problem is that even if the case is too tiny, so even if there is a very high efficiency of power conversion, then still there is some power dissipation going on. If the case is too small, then we start to have problems with dissipating the heat from this super small case. Here, take a look. Here we have in the normal case. In this kind of case, we've got the thermal pipe under the chip. This is normal picture of the DC-DC converters, and the thermal pot is important. Even if this super tiny case, the thermal pot is exposed, and then you can solder the thermal pot, then the problem begins that the case is so small that the thermal pot and the copper around has to be large enough to dissipate the power inside of the case. So you gain on a super tiny case, but then you lose on that area that you have to sacrifice for the heat dissipation, for the radiator. Of course, today switching regulators is just one part of the problem, because very often we like our embedded systems to be battery operated. And with battery operated, we've got two cases naturally today in standard embedded systems, so we can use non-rechargeables and rechargeables in our applications. With non-rechargeables and rechargeables, again, we've got today a couple of options. In case of non-rechargeables, the standard one is are the zinc or alkaline batteries. These are the standard technologies. So those batteries, so zinc carbon alkaline, so you can find them in shops everywhere. They are available in variety of sizes. And with this non-rechargeables, we can count on 1.5 volts from the beginning, and then the cell can drop even below below 0.9 volt per cell. And here, in case of battery operated circuits, two important things. First thing, this option. So voltage regulators here should be avoided. And if you really need a voltage regulator, use switching regulator only this time. So batteries are, from practical point of view, a fantastic source of very clean power supply. So even with linear regulators and with linear power supplies, you are not able to get as clean output as out of the batteries. So the batteries are a fantastic source of noise-free power supply. And yeah, but the problem is that the voltage drops here, especially with zinc carbon and alkaline batteries. Yeah, which means that we have our circuits to be designed appropriately to handle this voltage drop over its lifetime, so the lifetime of the battery. So in general, we need some kind of supply supervision circuit. So we need to have a circuit that would check the voltage and reacts accordingly. The voltage goes below certain threshold. But the regulators should be avoided anyway. So they should be avoided because linear regulator is a waste of energy. And switching regulator, using switching regulators with clean source of energy as a battery is a very bad idea. So two things: voltage regulators should be avoided, and supply supervision circuit kind of necessary. We have on the market those batteries available in standard cylindric sizes, so like AA, AA, AAA, B, C, D, this kind of things, you know it very well. A new thing in the world today that is becoming more and more useful are the lithium batteries. The lithium batteries available in non-rechargeable non-rechargeable lithium batteries, various technologies. So they are. So lithium, they have lithium inside, but a combination of lithium with some various elements. The good thing about the lithium is exactly the super discharge capability, because that's what we can get from the lithium battery. So the voltage is higher, but the voltage, take a look, the voltage is usually constant or almost constant throughout the discharge cycle. Here is an example of one of the battery characteristic with discharging over not very high current, because it's 10 milliamp here and 10 microamps here, but for the battery operated device, that's okay. And still we've got the banding is really at the end of the life cycle, which means that the supervising of such a lithium operated circuit is simpler. The problem of lithium batteries, the problem is the differences between the batteries, because you can find on the market. So the lack of standardization, I would say, because we have on the market really values with 3 volt, 3.3, 3.2, 3.6. Of course, they are similar, but still it's something different. So it means that you need to be careful which manufacturer you rely on when you are designing something new. And another problem with lithium batteries is the pricing. So they are better because they are lighter. They are maybe not safer, but they are lighter. They have super discharge characteristic. Yet the price is usually still it should change because it's changing. A couple of years ago, normal good alkaline battery cost was about 10 zloty, and the lithium was about 100 or more than 100. Today it's much more comparable, although still zinc carbon are dirt cheap. The alkaline are maybe not dirt cheap, but they are cheap. In case of lithium, unfortunately, it's not so. So it costs still a bit. In case of the rechargeable batteries, what's the main problem of the use of rechargeable batteries in practice? How do you think? Maybe the question to you. Because we have non-rechargeables, rechargeables. What's the problem of rechargeables? Why not choose rechargeables all the time? Why not? Why to think about non-rechargeables at all? Because rechargeables are we can charge them and we can renew them, so their lifetime is infinite theoretically. At least with rechargeables, we could deplete them. We have to throw them away. So why the rechargeable? What's not good with rechargeables? How do you think?
Because it's some kind of series to charge them, they have more space because of that.
We can't hear you. Could you speak up louder a bit? Yeah, Jakob answered on chat. First, the problem is the pricing. Of course, the rechargeables are more expensive, but that's only part of the problem. In my opinion, the most difficult thing is that we need to add a charger. From practical point of view, we need to add a charger. In non-rechargeables, we are just putting a place for batteries in our embedded system, and it's done. It's working. With rechargeables, a very good practice is to build in a charger so that you can, the user has the device and can recharge the batteries in the device. Of course, you can make just a place for the batteries and force the user to use external rechargers, but then, yeah, today nobody likes this kind of solution. So, of course, the pricing of the cell itself is steeper, is higher, but in my opinion, more important and worse is that we need to put a charging circuit. So, two technologies. Three technologies today available. So we've got nickel cadmium and nickel metal hydride still available in the market. So this kind of rechargeables, and lithium ion, lithium polymer cells, which is the second category. Although again, lithium, the batteries with lithium and something, there is more that we have no time to get deeper into it, but there are a couple of options, like with ferrum, for example, and some others. The lithiums, the advantage of lithiums comparing to lithium based batteries, there are two advantages of those. So maybe not even more than two advantages today. So in case of lithium batteries, they are definitely lighter. They are more expensive, of course, but the lithium batteries are lighter and they offer much higher power density than the nickel metal hydride, because today I think that because of cadmium, they are forbidden today in sales. So it means that we've got an AMH batteries, but still they are cheaper, but heavier, and as well, interestingly, one more practical feature is that they are cylindric, while the lithium batteries are available in cylindric cases, but they are quite often available in prismatic cases. That's nice, I would say, because it's easier to build in a battery into a device with prismatic cell, because you don't lose the space. You don't need to design something for cylindric battery. So we have this option. So that's also, in my opinion, kind of a good advantage of lithium batteries over an AMH battery. Lithiums are theoretically more dangerous, but yeah, so they have to be. So that's the problem of the charger itself. So that we need to design the charger in a safe way, so that we don't make the lithium neither explode nor deplete completely. Because in case of lithium, we have to avoid going in both directions. But the lithium gives us a future-proof design in case of lithium rechargeables today. So if you intend on building an AMH rechargeable, again, think twice. So that's, in my opinion, not good for new designs. You should go with lithium. Still, you need some chargers. In case of charging the batteries in the device, because that's the advantage of such a built-in charger, is that the case can be simpler. There's a lot of troubles of making a cradle for the batteries, because the cradle has to be strong. If it is to be used by a user, if it is to be opened, I don't know, once a day or frequently, then the cradle has to be strong. If we build everything into our device, no cradle necessary, because no accessible cradle. So we need to put the battery somewhere, but the cradle can be just assembled and it's done. So we don't need to make a complex and reliable construction here. Yet the problem of this is the charger itself. Why the problem is the charger? The charger, because we need not only when we construct a charger by ourselves, when we intend to do it, it's possible, but we need to control the battery voltage, we need to control the battery temperature, and we need to control how the temperature and the voltages are changing. So the charger itself has to monitor everything and has to apply appropriate current to the battery during various phases of the battery charging. Of course, this is possible, but safer is to use a ready charging chip. But then again, like with DC-DC converters in the market, we've got a variety of those chips. Maybe not such a great number. Fortunately, there are fewer of them. But still, they are minded. I don't know if you have met, but they are programmable chargers. So no, I'd say, if possible, avoid programmable chargers. However, it sounds as chargers, maybe the stupid element, but it's a simple element. Of course, it has to control everything. But programmable chargers from Texas Instruments, especially, a horrible thing, I would say. Yeah, normally the charging, if you want to build by yourself, here is the example of the lithium-ion 2-cell charger. It's not that trivial. It's not that simple. That's without the microcontroller example. Without the microcontroller with LM317 and 3420, so the reference itself. But it's the dedicated charger for those two Li-ion cells. They normally, we have to adapt to the cells that we are using and to the number of cells to the even manufacturers of the cells. So building a charger by yourself is always a tricky thing. Better idea is to use a ready charger. At best not programmable, but sometimes it's the only option. Here is a charger with I2C interface to a microcontroller, supplying up to two cells, because it really depends if we have one cell or 2 cells or 3 cells, and then charging of 2 cells or 3 cells or 4 cells requires special connection and special chargers. So again, using a charger that we have that is ready, that is somewhere around us, is the best solution. In case of clocking, because if we have the power supply, so the next one is clocking. Clocking is surprisingly simpler. We talked about it, so today we've got basically just 3 options. So we can use either the external crystal oscillator with decent stability, yet requiring 2 capacitors and a crystal. The problem with external crystal oscillator, besides requiring the C1 and C2 capacitors, is the limited frequency of the major crystal, because the crystal oscillation is cut dependent, and because of this, the first harmonic is only up to 26 megahertz, above 25. Above this frequency, we need to use third harmonic or fifth harmonic, which is always weaker, and there's a problem with the crystal resonating at different frequencies. So basically, this crystal oscillator is useful today in a limited number of cases, basically only when you need 8 or 6 or 16 or 24 megahertz, period, nothing else. If you want today more and more useful are the internal RC oscillators. They used to be limited to a few megahertz range, but that's not true today. Manufacturers improved the RC oscillators so much that we can find even 64 megahertz on board, on chip. Of course, they are cheaper because we need no components. Everything is integrated inside. They have low stability, and that's the problem. And then sometimes they need a calibration. That's another problem. So if you want to make a precise clocking, internal RC oscillator is never a good idea. So USB interface, UART interface, if you intend to use them, don't go this way. So don't try even with internal RC oscillators, but yeah, don't try. Again, I saw a synchronization circuitry for the clocking for the USB itself. So to make USB running from internal RC oscillators. So it is possible. People like internal RC oscillators because they are cheap, because they don't, no additional component count is necessary. Therefore, I would suspect more developments in this range in the future in case of internal RC oscillators. Of course, traditionally we can use external clock, but today, traditionally, on my list, I would put it as the second solution. So the internal RC oscillator wins on my list because it's the cheapest, it's the simplest. Yet, if I need more stability, then external clocking is a good solution. Of course, we don't talk about the ultra high stability clocking, so that's not, of course, the case. But the standard external clocking oscillators, TXO, TCXO, or even OCXO, so oven controlled crystal oscillators, they deliver excellent stability at decent size and decent price and too high power consumption, but still very good. The trade-off is so then all in general it's a good it's an pretty optimal solution. So on my list this would be a solution number two. The external crystal is not a good solution. It's not a preferable solution for the reasons I told you already, at least for me. And naturally, if possible, we should use a PLL. We should use onboard phase lock loop. And those PLLs give us a possibility to reduce the EMI generated by the microcontroller itself. Especially if we talk about a couple of hundreds of megahertz microcontroller, then generating those 200-300 megahertz on the PCB means that we will be having some PCB track that will work as an antenna and will start to emit those hundreds of digital switched high frequency signal to ether and to all the devices around. So much simpler, cleaner solution today is to generate a base 8 megahertz clocking with a crystal oscillator, stable crystal oscillator, and then multiply this clocking with an internal PLL. So that's the way we do it today. So usually this is the preferable solution with external clocking and the PLL integrated. In case of the stability depends on the clock source and jitter of PLL. So if the clock source is stable and the jitter of the PLL is low, then the stability can be pretty good. Resetting circuitry. This is usually pretty simple. So the simplest solution is just to make this kind of resistor, which is again optional. So the reset doesn't have to be connected at all. Although from practical point of view, even if this is optional, less optional is this capacitor. It's not given on data sheets very often, but it's a really good practice to add a capacitor here. What's the range of the capacitor? I usually put here or recommend here about 10 nanofarads. So that's something I would recommend. More or less, it can be something between 1 and 100. So 10 nanofarads usually is good here because of the rule of the thumb. Why do we need this capacitor here and not even the resistor? The capacitor is to dampen the spikes that may occur on the inputs, on the pins of the microcontroller, especially on the reset pin of the microcontroller during normal operation, especially in the presence of strong electromagnetic components, electromagnetic fields, like, for example, motors. They can generate spikes. The spikes may reset the microcontroller. So it's really safer to put a capacitor here without thinking. You know, the resistor is sometimes not necessary, so we can put it, we can avoid it. That's usually not the problem. But the capacitor is really a good idea to put it here. The same version is to do it like this one with additional diode for damping the over voltage, so for protecting, because this diode is for protecting the reset circuitry against overvoltage, against spikes exceeding VDD. It's a very safe version. In my opinion, that's not really so necessary. Also, in case of the resetting, sometimes you can find solutions including a special reset monitor chip. The reset monitor chip, that its role is to generate a reset signal with a time shift against VDD, and as well to filter out the spikes and various interferences appearing on the VDD line, so to deliver a clean reset signal. Today, that's not that important. The microcontrollers today include this kind of circuitry already inside the structure, so we can really avoid using this chip in reality. Okay, let's have a short break. So we meet in 15 minutes with further remarks about the construction of embedded systems. Okay, welcome back after the break. Next thing to connect, programming pins. Programming pins, the thing that is depending really on the microcontroller, because depending on the particular architecture, there exist a couple of methods of internal flash programming. Classic method is to use a JTAG. JTAG interface, so 5 pins there, need to be connected to the ITDO TMS TRST and ground. The problem with JTAG from practical point of view is that we need to have this kind of interface available. This kind of interfaces got cheaper over time, so today JTAG is not such a problem. But sometimes it's still expensive. Therefore, quite often in microcontrollers, it's possible to use for programming simpler interfaces. It has an advantage as well. So simpler, like the standard is UART, but also USB today, SPI sometimes for programming. This is useful. This is cheaper. Yet the important disadvantage is that it's only for programming. Only for programming. For rapid programming, sometimes we have also a parallel interface used, because inside the industry, if you need to program thousands of units per day, then serial programming of a UART is not good enough, not fast enough, so sometimes parallel. Yet for the development today, sometimes besides JTAG, we've got the dedicated interface for programming and debugging. In all cortexes that we have around us, there is available SWD, which means that it's simpler version, it's just 2-pin version compared to JTAG, easier to use, and not only for programming but also for debugging. Problem solved about the debugging in standard UART interface or USB interface used for programming. It's just programming minded, no debugging. So for debugging, JTAG or SW or SWD. Then we need to find, in case of programming, we need to find, of course, which pins are connected to what. And very often in microcontrollers, we've got this kind of boot mode selection table. So sometimes this table is simpler. Sometimes we've got just 2-bit mode selection. Sometimes it's just 1-bit mode selection, which means 2 modes. I found the microcontroller. So this is from Texas Instruments portfolio with 16 modes of boot mode. And then there are modes about using UART, using SPI for programming, I2C can be used in this processor, or Mac BSP for programming external interface, so for parallel programming, 32-bit even, parallel boot as well. So a couple of versions about the boot. Important from our perspective, from the perspective for the designer or developer of embedded systems, is to localize this kind of table. Localize this kind of table and search for this, because if we want to use UART programming or SPI programming, then of course we need to find out how to make this. What is necessary to start the processor in this mode. But considering that we are using SWD or JTAG, which are separate pins, then still we need to find this table, and still we need to, in this table, localize how to make the processor running from flash, and especially which pins are to be set appropriately. So from practical point of view, we need to find this table. We need to localize it. We need to find in this table which GPIOs should be configured in which way during reset, because this is during reset. After the reset, those pins become general purpose IO. But again, sometimes it's again a pitfall especially if on those pins there is a dedicated SPI or UART or whatever interface that we intend to use later on during the functioning of the device. And during reset, it has to be configured strictly to 111, for example. Anyway, this table has to be found and has to be analyzed. Connecting general I/O pins in a microcontroller. So this internal structure, the standard one. So we talked about it again during one of the lectures. Previous semester, as far as I remember. The things to remember about this port structure, universal ones, are first of all that there is kind of protection on the pin. The protection means that there is some clamping current that must not be exceeded, because the clamping current is protecting the rest. So the rest of our device, of our pin, against breakdown. Then we have two parts. We have input and output. In case of output, can be push-pull, can be pull-down. In case of pull-down or open collector version, pull-down. In case of open collector version, this transistor is switched off. We have just NMOS in the path, and we need to add a pull-up, either internal or external pull-up for operation. For example, I2C, SDA, SCL pins require this kind of configuration. Additionally, we may have some analog functionality of the port. It really depends on the microcontrollers. Some microcontrollers have universal ports that, like here on the slide, that have mixed digital and analog signals. But there are some microcontrollers with dedicated analog inputs. So the pins that, if not used for analog purpose, must not be used for anything, or are useless for anything else. This is the that's how it works. Important thing today is that depending on the capabilities and requirements, MCU pins can drive load either directly or through a driver. Through a driver, it's pretty normal. Yet directly, it depends what you need to drive. Normally, the loads that we can attach to the microcontroller should be below 10 milliamps. So that's the current that microcontroller can handle. Although today, you can find sometimes in some microcontrollers even pins with capabilities of handling 100 milliamps or so, or similar value. 100 milliamps is pretty high current. The thing to remember here, and my warning, is that this is single pin, but there is a limitation of the total current flowing into a microcontroller. So if you intend of using multiple pins with high load, then you may break the processor itself because of exceeding this maximum current. That's the problem. Then in those situations, you should use a driver. A driver, what's a driver here? A driver, usually it's, so two types of drivers. First, closed one, this magic triangle. How such a magic triangle is called? Who knows? Oh, this one. What's the name of this element? Who knows? The name of this element, this triangle. You should know this element. This is a negation, right? So this is not.
A buffer?
Of course, this is a buffer. A buffer that is basically transforming the impedance or reducing the impedance of the path. If a microcontroller output impedance can be modeled with a couple of hundreds of ohms usually, then the output, the driver, can be modeled with a few ohms impedance. So it depends on the drivers. So there are better and worse drivers, but it can be used. But that's the simplest. That's the simplest way. The disadvantage of the driver, pricing. I'd say this way. Second option, of course, is to use a transistor, because the transistor can be a driver, yet the transistor, both in this configuration, so input output, and in this configuration, so with CMOS and some resistor here, they have two disadvantages, both bipolar driver and CMOS drivers. The negation of the signal, because that's how they work in this configuration, that if there is a 0 at the input, then there is high state at the output, and if there is a 0 at the output, a high state at the input, then there is a low state at the output. So we've got our signals from microcontrollers are negated through these drivers, which means that they are equivalent to the NOT gate and not to this buffer. In case of bipolar transistor, we are missing here a resistor. The resistor is important in this configuration. The resistor is important. Why is that so? Oh, that's a question. Who knows? Why the resistor is important here? Why is the resistor, series resistor, important in the bipolar driver configuration? Who knows? Base emitter voltage here. Base emitter voltage, even with a completely open transistor, is on the level of 0.8 volts. If our microcontroller has 3.3 volts or even 2.5 volts voltage value, then still it doesn't match. So this 2.5 and 0.8 doesn't match. So there must be an element where there will be a voltage loss. If you don't use this resistor, that's the problem. If you don't use this resistor, the voltage loss will be on internal impedance of the microcontroller, which is not good because it will heat up the microcontroller. So if you intend to use bipolar drivers, then use the resistor. For most drivers, for MOSFET transistors, it's not necessary. MOSFET transistors, the current is not flowing only during start. And to be honest, here the resistor makes more harm than good in case of bipolar. In case of MOSFET, because the resistor, series resistor, slows down the switching of the MOSFET transistor. So for bipolar, resistor series one. For MOSFET, you connect a MOSFET directly to the pin to form a driver, or you use a buffer for this purpose. And the buffer is necessary today, maybe not for LEDs, because as you can see, the LEDs, the basic circuit of connecting LEDs just use a series resistor and connect the LED. So we don't need a driver to switch on the LED. In old microcontrollers, but you won't find them on the market. The LED has to be connected in this kind of circuitry. This direction. This kind of circuitry. This is the simple solution of driving the LED. Although this solution is still viable if the LED is to be supplied with the current value exceeding the capabilities of the I/O port of the microcontroller. So, for example, you want to make a very strong LED with half an amp or an amp, and then you should use this kind of circuit. Although this kind of circuit, no, it's okay, because I thought about bipolar and CMOS, but there is no difference. There is no difference here. So here I have the example of supplying the multiple LEDs out of the microcontrollers. We've got a series resistor, some basic power bipolar transistor, and the LEDs which are driven here. Of course, there is a series resistor in order to limit the current flowing through the diodes, because we found this resistor, depending on the voltage at this point, it would be possible to burn the diodes, burn the LEDs. So with the series resistor, it's not. Then we can regulate the brightness of the LEDs and we can protect them against overcharge and against breaking them down. Yeah, transistor-based current will take all of current it can. Sure, you're right. That's about the chat message. Good. The MOSFET transistors do not require the connection of the microcontroller of series capacitor, yet it's a good practice to add a parallel one. And the question is, why? Why the R2 here? Why the parallel resistor between the gate and the source in MOSFETs? Series, not important, but why the parallel?
For discharging internal capacitor between the gate.
Very good. And then discharging, so if we discharge faster, so then what we obtain with this? So faster discharging of the capacitor, what it will give us?
Shorter fall time?
Yeah, switch off will be faster. Because the switch off will be faster, because then the charge will not be kept at the gate, but will be discharged by this resistor. So the switch off time will be faster. Especially today when we have these transistors with very high impedance of the gate, this resistor makes the difference. Okay. Special pins of microcontrollers. A booby trap, standard booby trap in every microcontroller, because we've got 200, 300 pins, and there is one or two special pins which need to be connected extra. Sometimes it's not even written that they must be connected, but it's written that they should be connected. That well, should be replaced by must in many situations. The problem is that localizing this pin sometimes it's pretty difficult. Take a look. We've got this pin PN, for example, which needs to be connected appropriately, otherwise the microcontroller won't work. Then another example, VICA, in one of the STM8, if I'm not mistaken, microcontroller. Again, the pin, which is, yeah, it's not stated that it needs to be connected something to this pin. Okay, it's written somewhere that needs to be connected, but then well, who cares? So I didn't use this feature. Why to connect anything there? But then if you don't connect it, it's not gonna work. Another example, boot pin. We talked about the boot pin before. So the boot pins in general has to be localized and properly connected. Otherwise, our application won't work properly. Then we've got again the pins in microcontrollers which needs to be connected, like various power supply pins. Especially it's true for the analog block, but small. The problem with those pins quite often is that in some situations you don't need to connect them. But in some microcontrollers, for some unknown to me reason, even if you don't use analog circuitry in a microcontroller, you have to configure those pins. Here in this example, these are those two pins and those three pins, actually. And if you don't connect anything to those pins, even digital part of the microcontroller won't work. Why? No bloody idea. But unfortunately, sometimes it's so be quite careful about it. Case choice. And so something that could be done a bit earlier, but can be done as well at this stage. So basic rules, according to me. Choose such number of pins that functionality of your embedded system is not quite obvious. So we should choose a case that is large enough to include all the functionality that needs to be delivered. And naturally avoid deep cases unless you intend to use a breadboard. So for the breadboard deep cases, for all the others, not really. The deep cases are huge today. Although usually we don't have this kind of problem because I don't know if any new processor on the market is in deep case. Maybe deeps are that generally. And then avoid CSP and LGA cases unless you have special equipment for soldering. This is for amateurs. I met many examples of proto boards with unnecessary small cases. We talked about it a bit before, so I won't repeat it. So, but the good cases are QFP and QFN, to be honest. Deep, not really, because QFN is small, but it's still manageable. QFP is, the size is proper, in my opinion, so very good. In case of SO cases, they also do their job, although they are pretty large. SOT maybe is smaller, but SOT is just a few pins. The case that can be considered, in my opinion, is BGA. The BGA case, although there is required a hotter or an oven, but the BGA can be adapted. Yet, in case of BGA, be pretty careful if here you have a microstar, which means that the distance between balls is 0.5. So again, this is something for me no-go. On the market, they are 0.8, which is the standard, and 1 millimeter, which is pretty large case. But so it seems not such a difference. So what's the difference between 0.8 and 0.5? But yeah, please try to make a PCB of this dense BGA. You will see by yourself. So 0.5 is usually no go because it's PCB. It's too expensive. So you need to then start using 4 mils. 4 mils tracks. So it's 100 micrometer tracks. Very fragile. Okay, possible. Okay, today there is technology. JCL PCB will do it. Yeah, think twice about it. DFN, even smaller case as well, possible because it's similar to QFN for a small pin count. This DFN as well, it would do. So then we have our microcontroller, and then the vital part of our lecture, so connecting sensors to an MCU. In case of various sensors in microcontrollers, we don't have sensors unless we treat as sensors voltmeters or I don't know, some timers. Normally, if there are any sensors, then it's just the temperature of the microcontrollers. The sensor added for protection, nothing else. In case of external sensors that we are connected, we have a couple of types of sensors. First of all, the sensors with analog output that is single-ended or differential. And depending if the sensor is outputting single-ended or differential signals, then we have to either we can connect it directly to a microcontroller or we can use a circuit. With analog, a circuit which we call a signal conditioning circuitry. Then second group of sensors are sensors with digital interface. And in case of sensors with digital interface, we've got usually serial interface. Sometimes there is parallel, but not really often. So usually in case of digital interface, SPI or even I2C is good enough because mostly we talk about sensors which are pretty slow, which measure once a second or in this time scale, which means that we don't need really the parallel interface and the throughput we get with this interface. So then it's enough to use the SPI and I2C interface to connect to this kind of a sensor. Some examples of the sensors that we can connect to a microcontroller first from the line, so something you had last semester on the project, pressure sensor. At least those of you that did have it know it exactly, and the signal conditioning from the sensor, so the analog output and the power supply. And then the most problematic is the signal conditioning in this kind of sensors. We take then this kind of a chart of the characteristic, and so this is the pressure to the output generated by the sensor. And first of all, we read from the characteristic more or less the range we are going to use. So, for example, this range. Then we read from here to here, what's the output voltage range. So this is here from 2.8 to 4.2 volts. And then we've got the input, which is 0.0 to 2.5 or 0 to 3.3. So we need to make some adaptation circuitry. Again, this is something you were doing previous semester. So just to sum it up, we need, even if we don't need to make any conversions of the offset and of the amplification, we still need, in fact, two things between the sensor itself and the analog to digital converter. So we need the anti-aliasing filter and the low impedance buffer. Low impedance buffer, so the anti-alias is necessary. So it's really a must. So yeah, it can be even two-stage, because here on this slide it's two-stage, because this is also AF. On this example, so there are two stages of the filter. The buffer is optional. Let's say the buffer is optional. It depends on the sensor. It depends as well on the impedance of the ADC. If the ADC has buffer inside, because there are certain ADCs with buffer inside, then we don't need external buffer. If the ADC is having no internal buffer, this op-amp becomes important. What happens if we don't use the op-amp? Then the linearity will be hardly affected of the measurement. Linearity will influence, of course, the functioning and the quality of the reading. So the buffer is really required, plus at least one anti-alias filter to get rid of the unwanted noise. In case of the filter, the filters, sometimes we don't use just a simple RC filter. Sometimes we want our sensor to have more complex characteristic. So we can either design a kind of a low-pass filter with a sharp characteristic, but also we can. In some sensors, we are not interested in the DC signal, but for example, we're interested in some frequency signal, I don't know, from 10 kilohertz to 20. So then we can use a Butterworth, Chebyshev, or there are many structures of the filter. There are many tools for designing the filters. You can, of course, do it manually, but there are tools that helps us in design and simulation of this kind of filters and finding out why there are such horrible values here, and maybe to optimize. So then you take the LT spice, make the optimization, and so on to find the most suitable solution. Another example, a bridge, standard example, a bridge with where the voltage is differential, because the voltage is taken from here. This kind of bridge sometimes can be connected to a microcontroller directly, but the microcontroller must have fully differential ADC input. But usually we need some conditioning, because the level, the offset, and the impedance of this kind of signal is quite often not right, and we need to add it. In case of if we need to change the offset and the gain of our sensor for single-ended this time, single-ended operation, then we can do it generally in a few ways. With op-amps, there are two ways of doing it in a simple circuitry. One way is to add the offset at the negative input. Another solution is adding the offset at the positive input. Where are we using which solution here? Where are we using solution A, and when are we using solution B? Solution A is used in situations where the output, so when we have some negative voltage available on PCB board. So if we have negative voltage here, and if there are two symmetric supply of the op-amp, so if we have VCC and VE, somehow positive and negative power supply. For single-ended supply, so for the situation that the op-amp on the board, we've got just VCC, just VCC, we're using this solution, then we don't need a negative voltage here as well. We are then changing, we can have, but we don't need to. Then we are changing the, it will work as well with single-ended power supply. Yet it really depends on the application. Sometimes, sometimes even in symmetric, in non-symmetric, we can use this solution. Of course, in symmetric applications with symmetric power supply voltage, we can use this solution. You've got on the slide the formulas for the Vout. The solution A is giving a simpler, actually in case of the offset regulation, because the offset is here non-dependent on R1. It's dependent on R2, but we can modify the amplification of Bin by modifying the R1, and if we keep the R2, then the offset will be dependent, will not be amplification dependent of the signal, while the solution B has the disadvantage that unfortunately the offset is fully dependent on R1 and R2. So we have to then, when designing this circuit, we have to then, when we modify even one thing, usually we have to modify a thing in an element in another branch in order to keep the offset and amplification profile proper. That's the problem of the solution solution B. Instead of using op-amps, a method that is sometimes used, a method that is not that bad, especially in case of differential bridges, are the instrumentation amplifiers. The instrumentation amplifier are three amplifiers connected in the way that you can see on the slide, where there are two input buffers with the summing amplifier A3. This connection of the amplifiers delivers the output voltage, which is dependent linearly on the difference of the input voltages, multiplied by some coefficients depending on the internal resistors of the instrumentation amplifier. If you would like to build this amplifier by yourself, what is important is the quality of those elements, then the quality, maybe not the quality, but the repeatability of those elements. So they should have a good tolerance. In case of the single chip solutions, it's done for us, so we are paying, but we get an instrumentation amplifier with the proper settings. And this kind of an instrumentation amplifiers you can then drive. Sometimes you can drive manually. So some instrumentation amplifiers have R1 or R2 somewhere available on the pins that you can modify. But sometimes it's I know a lot of instrumentation amplifiers which are driven either by DC voltage, so the amplification of the amplifier is DC voltage controlled, or is changed by digital interface. I2C, one wire, SPI, so various instrumentation amplifiers of this kind are available on the market. For signal conditioning, to be honest, using this solution is okay. Using this solution is better. More expensive, but better. Important elements, maybe not very important, but the important thing is that usually in case of ADCs, we've got pseudo differential inputs. Pseudo differential, which means that they are not fully differential, which means that the potential of single pin against ground has to stay within the limits for the whole microcontroller. So it means that we are not able to connect differential signal of 0.1 volt with potential of 40 volts, because we will damage the microcontroller. We are allowed only to connect something from 0 to VCC, or VCC plus 0 to volts. It has to be remembered and it has to be protected. For this reason, there are special drivers available for the microcontroller. The special drivers, like which can be connected, as you can see now on the slide, with some protection against over voltage, so that these buffers will then transfer the output of the buffer. So the signal here will be just the modified difference of the input, and it will survive the high potential of the inputs. The buffers I saw once a few times are capable of handling a potential here of even 100 volts, of even 100 or more volts here at the minus and plus input. Of course, the difference value between minus and plus had to be much lower, but the potential of the point 100 volts or even more. And thanks to such a buffer, we are protecting our op-amp, delivering the signal that is within the range, safe for the microcontroller. In case of digital interface, the sensors, because they are usually pretty slow, so it's usually SPI or I2C. Sometimes one wire, much more rare is UART. So these are the interfaces we have. In case of SPI, the problem with sensors, the main problem is that in order to connect multiple sensors, we need to use multiple lines. So that's standard thing. Yet the SPI, what we like the SPI very, very much is that it's very fast and the configuration is very simple, because it's enough to configure simple CPHA. Done. Baud rate, but the baud rate is not a problem in case of SPI. The baud rate is not much of a problem in I2C, but in I2C we need to configure the I2C a bit in order to configure the proper frame, the proper address, as well. What might be the problem in SPI are actually the addressing, so the small address space. But the good thing about the SPI is, of course, the connection. 2 wires always, whatever the number of slaves you have, just 2 pins. Don't forget about the pull-ups in case of SPI. They are not required, the pull-ups itself, because the master may have push-pull outputs, not a problem. But in case of I2C, the pull-ups are necessary. Important for I2C are the operation modes. So 4 operation modes, so don't forget about them. So the node and the master has to cooperate, and the master can work in master transfer, master receive mode, but can also be a slave transmitting or receiving. In case of the UART interface for the sensors, it's rather about modules. So it's not about single sensors. It's rather if you have some modules that are to be accessible from PC. So then they have UART, and then if you want to use them in an embedded system, then you have to use the UART as well. The problem with UART is that the baud rate is problematic. The baud rate, because we have asynchronous data transfer, the baud rate requires here usually the advanced clocking subsystem. Besides, there's required a voltage translation. So that's problematic. In case of the UART interface, my advice is not to forget about the control lines, so RTS, CTS, besides the standard RX takes, in order to be able to block the data transfer if any side is busy doing something. More often, to be honest, in case of sensors connection is one wire. One wire because it's slow, it's problematic, but it's just single wire. And the microcontrollers, if we spare on pins, if I2C is too abundant for us, then one wire could be a solution. So multiple sensors connection over single wire, very slow connection, problematic to be programmed. Yeah, but still, it's working. Besides, in case of the one wire, you should remember we've got this possible integrated power supply, which means that we can charge up the unused sensor, and then the sensor can use this energy during the operation. Something that is available in the aforementioned interfaces. Good. Okay, we've got next element of our lecture. So this is servicing. So how to handle the microcontrol, the sensors within our program, within our software. A couple of methods for it. Still, maybe not too many, but still, I would like to give you some advices about it, at least my notes about it, but that's already next week. So I would need about 10-15 minutes maybe, and we have just 1 minute, so it's not enough time. So we'll put a comma here and we'll finalize this subject, a few remarks about it already next time. Any questions? If no questions, thank you very much for your patience and your attention. See you next week. Have a nice day. Still.
Thank you. Goodbye.
Bye-bye.
Thank you. Goodbye.
Goodbye.